Have you ever stepped outside on a summer day and thought it couldn't get any hotter? Or shivered through a winter night convinced you'd never feel colder? What if I told you that the temperatures we experience here on Earth represent just the tiniest fraction of what the universe is truly capable of producing? Out there in the vast cosmic arena, temperatures reach extremes so unimaginable they defy everything we know about hot and cold. We're talking about conditions where matter behaves in ways that seem to break the very laws of physics as we understand them. From the frozen void of deep space where atoms nearly stop moving entirely to stellar furnaces so intense they make our sun feel like a candle in comparison, the cosmos operates on a thermal scale that will forever change how you perceive temperature. Picture this: somewhere out there right now, a dying star is collapsing under its own gravity, creating temperatures so extreme that for just a fraction of a second, it becomes hotter than every star in our galaxy combined. Meanwhile, in the emptiness between galaxies, regions exist so cold that they approach the theoretical limit of absolute zero, where particles virtually cease all movement. These aren't just abstract scientific concepts, they're real phenomena occurring across the universe at this very moment, each telling a fascinating story about how nature pushes the boundaries of what's possible. The sheer range of temperatures out there spans more than 30 orders of magnitude, creating environments so alien that if we were to experience them directly, they would be completely incomprehensible to our human senses. In this journey through the universe's most extreme temperatures, we're going to explore 30 mind-blowing facts that will challenge everything you thought you knew about heat and cold. We'll venture from the chilling depths of space's coldest regions to the unimaginable heat generated by the universe's most violent events. You'll discover how scientists measure temperatures that defy conventional instruments, learn about exotic states of matter that only exist under these extreme conditions, and understand how these thermal extremes have shaped the very universe we inhabit today. This isn't just about big numbers, it's about understanding the fundamental forces that govern our cosmos and discovering how temperature extremes have written the story of everything from the birth of stars to the fate of the universe itself. So prepare to have your perspective on hot and cold completely transformed as we explore the most astonishing thermal phenomena the cosmos has to offer. Our journey into extreme temperatures begins not with unimaginable heat, but with the profound cold of a theoretical limit. This is absolute zero, the ultimate bottom of the temperature scale, sitting at negative 273.15 degrees Celsius or 0 Kelvin. It represents a state of perfect stillness, a hypothetical point where all molecular motion ceases entirely. Atoms would simply stop vibrating and thermal energy would be completely absent. It's the universe's ultimate cold shoulder, a state of being so still it's almost impossible for us to truly conceptualize. Yet here's the fascinating paradox that forms our first astonishing fact. Absolute zero, despite being a clearly defined value on our temperature scales, is fundamentally unattainable. According to the third law of thermodynamics, it is impossible for any system to reach absolute zero through a finite number of operations. Think of it like trying to perfectly balance a pencil on its tip. You can get it incredibly close to perfect balance, but the slightest air current, the tiniest vibration, will always knock it over. In the same way, scientists can remove almost all the energy from a system, but they can never remove the very last minuscule amount. The act of measuring the system, or even the faint whisper of background radiation from the Big Bang that permeates all of space, constantly introduces tiny amounts of energy. This hasn't stopped physicists from trying to touch this ultimate cold. In laboratories around the world, using incredibly sophisticated equipment like laser cooling and magnetic traps, they have managed to cool atoms to within a fraction of a billionth of a degree above absolute zero. At these temperatures, matter begins to behave in bizarre and wonderful ways, entering states like Bose-Einstein condensates where atoms lose their individual identities and act as a single quantum entity. These experiments are conducted in ultra-high vacuum chambers, shielded from nearly every external influence imaginable, and yet that final, elusive step to 0 Kelvin remains forever out of reach. It's a testament to the fundamental laws of our universe, a boundary set by physics itself that we can approach but never cross, making the quest for ultimate cold one of science's most thrilling and endless pursuits. While absolute zero remains a tantalizing theoretical limit that we can only approach in laboratories, nature itself has created a place that comes breathtakingly close. Out in the vast expanse of interstellar space, roughly 5,000 light-years from Earth in the constellation Centaurus, lies the coldest known natural place in the entire universe, the Boomerang Nebula. This remarkable cosmic structure holds the record for the most frigid natural environment ever measured, with temperatures plunging to a staggering -272 degrees Celsius. That's just one single degree above absolute zero, making it significantly colder than even the deepest, darkest voids of empty space between galaxies. What makes this nebula so extraordinarily cold is a fascinating physical process happening at its core. The Boomerang Nebula is a protoplanetary nebula, a specific phase in the life cycle of a dying star similar to our own Sun. As this star exhausted its nuclear fuel and began its final transformation, it didn't go quietly. Instead, it began expelling its outer layers at truly astonishing speeds. The gas is streaming outward at about 164 kilometers per second, which is nearly 10 times faster than typical nebula expansion. This creates an effect similar to how our own breath feels cold when we blow it rapidly through pursed lips. The rapidly expanding gas undergoes adiabatic cooling, where the sudden drop in pressure causes the temperature to plummet dramatically without any heat being lost to the surroundings. Imagine the entire nebula functioning like a colossal cosmic refrigerator, with the expanding gases creating a massive cooling effect that chills the surrounding region to near absolute zero conditions. This extreme cold presents a fascinating cosmic puzzle because space isn't completely empty, it's filled with the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates everywhere in the universe at a steady temperature of about -270.42 degrees Celsius. Normally, this background radiation acts as a universal minimum temperature, a thermal floor that everything in space eventually equilibrates to. Yet the Boomerang Nebula manages to be even colder than this universal baseline, creating a localized pocket of profound chill that defies the ambient warmth of creation itself. This is only possible because the nebula's expansion is so rapid and efficient at cooling that it actually undercuts the temperature of the surrounding radiation field, making it the only known natural object in the universe that is colder than the background temperature of space itself. This astonishing achievement of natural cold pales in comparison to what human ingenuity has accomplished right here on Earth. While the Boomerang Nebula holds the natural record, scientists in laboratories have created environments that are orders of magnitude colder, reaching temperatures within a few billionths of a degree of absolute zero. To put that into perspective, these man-made deep freezes are over 100 times colder than the Boomerang Nebula, and even colder than the average temperature of the universe itself. This isn't just about breaking records, it's about creating conditions that allow us to observe the universe's most bizarre quantum behaviors that are usually hidden at the warmer temperatures we experience in everyday life. The primary tool for achieving these unbelievable temperatures is a remarkable technique called laser cooling. The process begins with a small cloud of atoms, typically rubidium or sodium, contained within an ultra-high vacuum chamber to eliminate any interference from other air molecules. Scientists then bombard these atoms with lasers from all directions, carefully tuning the laser light to a frequency just below the atom's natural absorption frequency. As the atoms move toward a laser beam, they experience a Doppler shift that makes the light appear to have the correct frequency for absorption. Each time an atom absorbs a photon of light from the laser, it receives a tiny push in the opposite direction, effectively slowing down. Since temperature is fundamentally the measurement of atomic motion, slowing these atoms down directly correlates to cooling them. After millions of these photon collisions, the atoms are moving so slowly that their temperature plummets to within a few thousandths of a degree above absolute zero. But the cooling doesn't stop there. The coldest temperatures are achieved through a second stage called evaporative cooling. The laser-cooled atoms are transferred to a magnetic trap where the most energetic atoms, essentially the hottest ones, are allowed to escape, much like how a cup of coffee cools as the most energetic water molecules evaporate away. The remaining atoms collide with each other, redistributing energy until they reach equilibrium at a much lower temperature. Through this meticulous process, scientists have reached temperatures as low as 38 picokelvin, that's 38 trillionths of a degree above absolute zero. At these extremes, matter undergoes a dramatic transformation into a new state called a Bose-Einstein condensate, where atoms lose their individual identities and merge into a single quantum wave, behaving not as distinct particles but as a collective superatom that displays the weird and wonderful properties of quantum mechanics on a visible scale. Leaving behind the laboratory's quest for ultimate cold, we venture to a world where temperature doesn't just drop to incredible lows but soars to astonishing highs, often within the same day. Welcome to Mercury, the solar system's champion of thermal mood swings. This small, cratered world, sitting closest to our Sun, experiences the most dramatic temperature variations of any planet in our celestial neighborhood. During its long, scorching day, surface temperatures can rocket up to a searing 427 degrees Celsius, hot enough to melt lead and even zinc. Then, when its night side turns away from the Sun for weeks at a time, the thermometer plummets to a bone-shattering negative 173 degrees Celsius. That's a temperature swing of 600 degrees, a difference more extreme than between a blazing oven and a cryogenic freezer. This wild roller coaster of heat and cold isn't caused by Mercury's proximity to the Sun alone. Venus, for example, is much hotter on average but maintains a relatively steady temperature. The real culprits behind Mercury's thermal extremes are its two defining characteristics: a near-total lack of a meaningful atmosphere and an unusually slow rotation. An atmosphere acts like a giant planetary blanket. It traps heat, distributes it around the globe via winds, and moderates temperature differences between day and night. Mercury's atmosphere is so incredibly thin, scientists call it an exosphere, rather than a true atmosphere, that it provides virtually no insulating effect. Without this blanket, the surface is completely exposed to the vacuum of space. Any heat gained from sunlight during the day radiates back out into the void with nothing to slow its escape once the sun sets. Compounding this problem is Mercury's rotational rhythm. A single day on Mercury from one sunrise to the next lasts an incredible 176 Earth days. This means its surface bakes under the relentless solar glare for about 88 Earth days straight, with all that thermal energy having nowhere to go but into the ground. When night finally falls, it also lasts for 88 Earth days, providing an immense amount of time for all that accumulated heat to radiate away into the blackness of space. It's the ultimate example of a world with no climate control, where the concept of a comfortable average temperature is completely meaningless. The story of Mercury's temperature teaches us a fundamental lesson in planetary science. An atmosphere isn't just about breathing. It's a planet's primary thermostat, its global heating and cooling system. Without it, a world is utterly at the mercy of its star, experiencing the raw, unfiltered extremes of heat from sunlight and the profound cold of space in their most potent forms. While Mercury's dramatic temperature swings showcase the extremes of having no atmosphere, our neighboring planet Venus presents the opposite scenario, a cautionary tale of atmospheric insulation gone catastrophically wrong. Venus holds the title of the hottest planet in our entire solar system, with a remarkably consistent surface temperature of 465 degrees Celsius. This is hot enough to melt lead, zinc, and even several types of metal, creating a surface environment more akin to an industrial furnace than a planetary landscape. What makes this fact so astonishing isn't just the intensity of the heat, but its source. Venus is nearly twice as far from the Sun as Mercury is, receiving only about 25% of the solar energy that bathes its smaller neighbor. By all conventional logic, Venus should be significantly cooler, yet it maintains temperatures that are actually hotter than Mercury's maximum daytime heat. The explanation for this planetary inferno lies entirely in Venus's atmosphere, which demonstrates the terrifying power of a runaway greenhouse effect. Unlike Earth's balanced atmosphere, Venus is shrouded in an incredibly thick blanket of carbon dioxide, with atmospheric pressure at the surface 92 times greater than what we experience here. Imagine the pressure you'd feel nearly a kilometer underwater, but combined with temperatures that would instantly vaporize any submarine. This dense atmosphere is over 96% carbon dioxide, a potent greenhouse gas that behaves like a one-way valve for thermal energy. Sunlight passes through the atmosphere and reaches the surface, where it's absorbed and re-radiated as infrared heat. Normally, some of this heat would escape back into space, maintaining equilibrium. But on Venus, the thick carbon dioxide layer acts as an impenetrable barrier, trapping this infrared radiation and causing heat to accumulate relentlessly over billions of years. This creates a positive feedback loop of terrifying efficiency. The initial heat trapped by greenhouse gases causes more water vapor to enter the atmosphere from surface liquids and minerals. And since water vapor is itself a powerful greenhouse gas, it traps even more heat, which releases even more water vapor. Scientists believe Venus may have once had oceans similar to Earth's, but as the planet warmed, these oceans began to evaporate, pumping tremendous amounts of water vapor into the atmosphere and accelerating the heating process. Eventually, the surface temperatures became so extreme that any remaining water boiled away completely, while ultraviolet radiation from the sun broke apart the water molecules in the upper atmosphere, allowing hydrogen to escape into space and leaving behind even more carbon dioxide. Without water to help regulate carbon dioxide through processes like rock weathering and carbonate formation, the way Earth's oceans absorb and store carbon, the greenhouse effect spiraled completely out of control, transforming Venus from a potentially Earth-like world into the hellish landscape we observe today. The story of Venus's extreme temperatures serves as both a fascinating planetary mystery and a powerful lesson about atmospheric chemistry. While Earth's greenhouse effect is essential for maintaining livable temperatures, without it, our planet would be a frozen ice ball averaging -18 degrees Celsius. Venus shows us what happens when that natural balancing mechanism tips into irreversible overdrive. Studying Venus's atmosphere helps scientists understand the delicate equilibrium that makes our own planet habitable and provides crucial data for modeling climate change scenarios. The same physical principles that turned Venus into a 465-degree pressure cooker are at work here on Earth, just on a much smaller scale, making our sister planet's extreme heat both a scientific wonder and the ultimate natural laboratory for understanding the limits of planetary climate systems. Moving from the steady, oppressive heat of Venus to our own star, we encounter one of solar science's most perplexing mysteries, a thermal paradox that defies basic intuition. If you were to reach out and touch the surface of the Sun, a region known as the photosphere, you'd encounter temperatures around 5,500 degrees Celsius. It's unimaginably hot, to be sure, but it follows a logical pattern. The sun's core is its furnace, and as you move outward, things should get cooler. Except they don't. As we rise above the visible surface into the wispy, ethereal outer atmosphere called the corona, the temperature doesn't fall, it skyrockets, soaring to a staggering 1 to 3 million degrees Celsius. This is the equivalent of stepping away from a roaring bonfire and feeling the air around you suddenly become thousands of times hotter than the flames themselves, a complete and baffling reversal of what common sense tells us should happen. For decades, this coronal heating problem has stood as a monumental challenge in astrophysics. The corona is the sun's crown, visible during total solar eclipses as a magnificent pearly white halo of plasma stretching millions of kilometers into space. This isn't a dense, solid region. It's an incredibly tenuous plasma, far less dense than the air we breathe. Heating such a diffuse gas to millions of degrees requires a phenomenally efficient energy transfer mechanism, one that can overcome the massive energy loss from radiation and still heat the plasma to such extreme temperatures. The puzzle lies in identifying the engine behind this heating. The energy clearly originates from the fusion reactions in the sun's core, but the process of transporting that energy outward and depositing it so efficiently in the corona has remained elusive, a cosmic secret hidden in plain sight. The prevailing theories trying to crack this mystery focus on the sun's complex and dynamic magnetic field. Unlike Earth, the sun isn't a solid body. It's a spinning ball of plasma with different parts rotating at different speeds. This differential rotation twists and stretches the magnetic field lines like strands of taffy, storing immense amounts of energy within them. One leading explanation for the corona's heat is a process called magnetic reconnection. Imagine two powerful magnetic field lines stretched taut and running in opposite directions, suddenly snapping and reconnecting into a new, lower energy configuration. This sudden rearrangement acts like a slingshot, explosively releasing the stored magnetic energy as heat and accelerating particles to tremendous speeds. It's a process so efficient that countless tiny reconnection events could be the invisible stovetop heating the entire corona. Another compelling theory points to the constant churning motion of the sun itself. The convective zone below the surface is a roiling sea of plasma, with massive bubbles of hot gas rising and cooler gas sinking. This constant bubbling motion acts like a trampoline, jostling the magnetic field lines anchored to the surface and sending powerful waves racing upward along them. Two types of waves are prime suspects: Elfvane waves, which are ripples that travel along magnetic field lines much like a wave travels along a shaken rope, and magnetocaustic waves, which are a hybrid of magnetic and sound waves. As these waves travel from the dense photosphere into the incredibly thin corona, their energy, which was spread out over a large volume, becomes concentrated. This energy concentration could then be dissipated as heat, much like how ocean waves crashing on a shore convert their energy into churning foam and warmth. The challenge for scientists is that these events are often too small or too fast to be observed directly with current technology, leaving us with compelling models but no definitive proof. Perhaps the most tantalizing proposal is the nanoflare theory developed by physicist Eugene Parker. He suggested that the corona isn't heated by a few large events, but by an unimaginable number of minuscule, undetectable explosions happening every second all across the sun. These wouldn't be the massive solar flares we observe through telescopes, but rather their incredibly small cousins nanoflares. Each one would release a minuscule amount of energy, but collectively, billions of them occurring constantly could provide the steady, pervasive heat source needed to explain the corona's extreme temperature. It's the thermodynamic equivalent of 1 million microscopic light bulbs instead of one giant spotlight. While we lack instruments sensitive enough to directly observe a single nanoflare, evidence from spacecraft like NASA, a solar dynamics observatory, suggests that a form of impulsive, bursty heating is indeed occurring, keeping this theory at the forefront of solar research. Unlocking this mystery does more than satisfy scientific curiosity. Understanding the Sun's atmosphere is crucial for predicting space weather that can disrupt satellites, power grids, and communications on Earth, making the solution to this hot puzzle vitally important to our technological world. While the Sun's corona presents a sustained, mysterious heat, Earth's own atmosphere produces moments of thermal violence that are equally extreme yet astonishingly brief. Consider the raw power of a lightning strike, a sudden, brilliant flash that can instantly superheat the air around it to an incredible 30,000 degrees Celsius. That's more than 5 times hotter than the surface of our Sun, a temperature capable of instantly vaporizing metal and fracturing solid rock. This phenomenal release of energy doesn't build gradually, it materializes in a fraction of a second, transforming a peaceful column of air into a searing plasma channel before vanishing almost as quickly as it appeared. The physics behind this instantaneous heat generation begins with the electrical charge separation within a thundercloud. As ice crystals and water droplets collide in the turbulent upper atmosphere, they create a massive charge imbalance, with the cloud's top becoming positively charged and the bottom gathering negative charges. This creates an immense electrical potential between the cloud and the ground, a difference that can reach hundreds of millions of volts. The air normally acts as an insulator, preventing the flow of electricity. But when the electrical field becomes too powerful, it violently rips the air molecules apart, stripping electrons from their atoms in a process called ionization. This creates a conductive pathway of plasma, a state of matter where electrons are no longer bound to their atomic nuclei, allowing a massive electrical current to surge downward in what we call a stepped leader. The incredible heat is generated when this leader connects with an upward streamer from the ground, completing the circuit and unleashing the main return stroke, the brilliant flash we see as lightning. An enormous current, often exceeding 30,000 amperes, explodes through this narrow plasma channel. This sudden, massive flow of electrons collides violently with air molecules, primarily nitrogen and oxygen, transferring tremendous energy to them in the process. These molecules become intensely agitated, vibrating and rotating at phenomenal speeds. It is this frantic molecular motion that we measure as extreme heat. The process is so rapid and energetic that it essentially creates a miniature star for a few microseconds, generating pressures up to 10 times greater than the atmosphere and producing the shock wave we hear as thunder. What makes this phenomenon so fascinating is its breathtaking transience. The 30,000-degree temperature exists for less than a millisecond because the superheated air expands explosively at supersonic speeds. This rapid expansion creates a cylindrical shock wave that instantly cools the plasma channel by dissipating its energy into the surrounding atmosphere. The entire thermal event is over before our eyes can even fully register the flash, leaving behind only the ozone scent of transformed air and the echoing rumble of its explosive birth. This dramatic cycle of creation and dissolution demonstrates nature's ability to concentrate unimaginable energy into vanishingly small moments, a fleeting reminder that even our familiar atmosphere can briefly host temperatures that rival the most violent cosmic events. Now let's journey from the fleeting heat of our atmosphere to the deep, enduring furnace at the very heart of our world. While we experience the sun's warmth on our skin, beneath our feet lies a heat source of truly staggering proportions, Earth's inner core. This solid ball of iron and nickel, roughly the size of Pluto, burns at an estimated 5,200 to 6,000 degrees Celsius. That's a temperature range that astonishingly rivals the surface of the sun itself. We are quite literally living on a planet that has a sun-like forge burning continuously at its center, a fact that transforms our understanding of our own world from a dormant rock to a dynamic, heat-driven engine. This incredible internal heat isn't merely a leftover from the planet's formation. It's a sustained fire maintained by two powerful and ongoing processes. The first is the primordial heat, the residual energy from Earth's violent creation over 4.5 billion years ago, when our planet coalesced from the dust and debris of the early solar system. Countless asteroids and planetesimals smashed together in a series of colossal impacts. The immense gravitational energy released by these collisions, compounded by the intense pressure as the planet grew, heated the young Earth into a molten sphere. While it has been cooling ever since, the insulating properties of the surrounding rock mantle have been so effective that an enormous amount of this formation heat remains trapped inside, like a planetary thermos keeping its contents scalding hot across geological eons. The second, and equally crucial, heat source is the continuous energy released by radioactive decay. Deep within the Earth's mantle and core are significant quantities of radioactive isotopes, primarily potassium-40, uranium-238, and thorium-232. These unstable elements naturally break down over time into more stable forms, and in doing so, they release a steady and substantial amount of thermal energy. This process acts like a built-in nuclear reactor, constantly generating new heat from within and replenishing what is slowly lost to space. Without this radioactive furnace, Earth's core would have cooled significantly more, potentially leaving our world as geologically dead as Mars. Together, this combination of ancient formation energy and ongoing radioactive decay creates a thermal engine powerful enough to drive the entire planet's geology. This immense internal heat is the fundamental driver behind every earthquake, every volcanic eruption, and the very movement of the continents themselves. The core heats the surrounding molten outer core, where the churning of liquid iron generates Earth's protective magnetic field. That heat then rises through the mantle, creating massive convection currents, slow, deliberate rivers of rock that flow over millions of years. These currents are the engine of plate tectonics. They push against the planet's crust, causing it to fracture into plates that drift, collide, and recycle. The Himalayas continue to rise, the Atlantic Ocean widens, and the Ring of Fire volcanoes erupt, all because of the relentless thermal energy working its way out from the core. This makes our planet incredibly rare and alive in a way that most worlds are not. That comforting ground beneath your feet is not static. It's the visible, cool surface of a fantastically hot and violently dynamic planetary system, all powered by a hidden fire as hot as the sun. But even the sustained furnace at Earth's core is dwarfed by the instantaneous, artificial inferno humanity has learned to create. The most extreme temperatures ever produced on our planet did not occur in nature, but in the heart of a nuclear explosion. At the precise moment of a thermonuclear detonation, for a fraction of a microsecond, temperatures at the fireball's core can soar to an almost incomprehensible 100 million degrees Celsius. This is a thermal spike so profound that it momentarily exceeds the temperature at the very center of our Sun, making it the hottest event ever generated by human hands and one of the most intense concentrations of energy in the known universe. This unimaginable heat is the product of two powerful nuclear processes working in terrifying concert: fission and fusion. The detonation begins with the fission stage, where the nuclei of heavy, unstable elements like uranium-235 or plutonium-239 are split apart. When a neutron strikes one of these large nuclei, it causes it to become unstable and break into two smaller nuclei, releasing more neutrons and a tremendous amount of energy in the process. These newly released neutrons then go on to split more nuclei, creating a runaway chain reaction that unfolds in mere nanoseconds. While immensely powerful, this fission reaction alone generates temperatures in the range of tens of millions of degrees hot but not yet stellar. The true thermal extreme is reached in the secondary stage, which utilizes the intense heat and pressure from the initial fission explosion to trigger nuclear fusion. In a thermonuclear weapon, the fission primary is used to compress and heat a secondary stage containing light elements, typically isotopes of hydrogen like deuterium and tritium. Under these extreme conditions of heat and pressure, the hydrogen nuclei are moving so rapidly that they can overcome their natural electromagnetic repulsion and get close enough for the strong nuclear force to take over, fusing them together to form helium nuclei. This fusion process releases an even greater burst of energy per unit of mass than fission. It is this moment of forced stellar creation, the same process that powers the Sun, that pushes the temperature to that staggering 100 million degree mark, creating a miniature star on Earth for the briefest instant. What's truly mind-bending is the timescale involved. This astronomical temperature exists for less than a millionth of a second. The fireball, having been heated to such an impossible degree, immediately begins to expand at an incredible rate, and as it expands, it cools with almost equal rapidity. The energy, initially concentrated into a space perhaps the size of a baseball, is instantly transformed into a blinding flash of light, a devastating shockwave, and a rapidly growing sphere of incandescent plasma. The sheer brevity of this thermal peak is a testament to the raw, uncontrolled power being released. It is an energy density so extreme that the universe itself cannot sustain it for more than a fleeting moment, immediately working to dissipate it across a much larger volume of space. This artificial sun is born and dies in the blink of an eye, leaving behind a chilling reminder of the destructive thermal potential we have unlocked. Yet even humanity's most devastating nuclear fire pales into insignificance when compared to the universe's ultimate expression of raw power, the supernova. This stellar cataclysm represents nature's own thermonuclear weapon, but on a scale so immense it defies comprehension. During the final, violent death throes of a massive star, the temperatures generated within the expanding shockwave reach an almost mythical 100 billion degrees Celsius. To even attempt to grasp this number, consider that it is over 6,000 times hotter than the core of our Sun, and momentarily creates a sphere of plasma hotter than the combined output of every star in the Milky Way galaxy. The journey to this thermal extreme begins deep within a star many times more massive than our Sun. For millions of years, it has fused elements in its core, first hydrogen into helium, then progressively heavier elements like carbon, oxygen, and silicon, each fusion stage generating the tremendous pressure needed to support the star against its own immense gravity. This process acts as a carefully balanced cosmic ladder, with each rung representing a new, heavier element and a hotter burning temperature, but the ladder ends at iron. Fusing iron does not release energy, it consumes it. Suddenly, the star's core loses the outward pressure that has sustained it for its entire life. In less than a second, gravity wins its billion-year battle, and the core collapses inward at nearly a quarter the speed of light. This collapse is so rapid and violent that it doesn't just stop when matter becomes densely packed. The inrushing material overshoots, compressing the core into an unimaginably dense ball of neutrons, then bounces back outward like a spring pushed to its absolute limit. This bounce creates a powerful shockwave that begins racing out through the star's outer layers. However, in a normal scenario, this shockwave would lose energy and stall, unable to tear the star apart. This is where neutrinos come in. The formation of the ultra-dense neutron core releases a staggering blast of these ghostly particles, so many that they carry away 99% of the supernova's energy. For a brief moment, a fraction of these neutrinos deposit their energy directly into the stalled shockwave, reheating it and providing the final, catastrophic push needed to explode the star outward. It is within this resurrected shockwave, a spherical wall of matter and energy moving at hypersonic speeds, that temperatures skyrocket to 100 billion degrees. At such phenomenal temperatures, physics operates under extraordinary rules. The environment is so energetic that it becomes a perfect crucible for the creation of the universe's heaviest elements. This process, known as explosive nucleosynthesis, is where the supernova truly becomes a cosmic alchemist. In the blinding heat and immense density of the expanding shockwave, atomic nuclei are battered by a torrent of neutrons. They capture these neutrons rapidly, climbing the periodic table in seconds to form elements far heavier than iron elements like gold, silver, platinum, and uranium. Without the unique conditions within a supernova shockwave, these elements simply could not form. Their creation requires a flood of neutrons so intense that it can only be provided by this universe-shattering event. Every ounce of gold in jewelry and every atom of uranium in a power plant was forged in a similar, ancient stellar explosion, making us all literally children of the stars. The release of energy is so titanic that for a short period, a single supernova can outshine its entire host galaxy of hundreds of billions of stars. This brilliance is not just from the incredible heat, but from the radioactive decay of the new elements created in the blast. The supernova scatters its newly forged heavy elements across light years of space, where they will eventually cool and become part of interstellar gas clouds. These enriched clouds are the raw material for new stars, planets, and ultimately, life itself. The calcium in our bones, the oxygen we breathe, and the iron in our blood were all created and dispersed by these magnificent explosions. A supernova is therefore not merely a death, it is a necessary, fertile destruction that seeds the cosmos with the fundamental building blocks for future worlds and ensures that the death of one star gives birth to countless others. But the universe doesn't stop at supernova. It takes the remnants of these explosions and forges them into something even more extreme. When the core of that massive star collapses, if it isn't completely obliterated, it can be crushed into one of the densest objects in existence, a neutron star. And the thermal story of these cosmic cinders is just as astonishing as their formation. A newly born neutron star, the hot heart of the supernova blast, emerges with a surface temperature of around 600,000 degrees Celsius. That means even after one of the most violent events in the cosmos, the leftover core is still glowing with a heat that makes our sun's surface look lukewarm by comparison. This incredible heat is a direct inheritance from the supernova itself. The core collapse compresses a mass greater than our sun into a sphere no wider than a city, about 20 kilometers across. All that gravitational energy from the collapse is converted into an unimaginable amount of thermal energy, essentially flash heating the newborn neutron star to these phenomenal temperatures. The density is the key to understanding its thermal behavior. A single sugar cube-sized piece of neutron star material would weigh billions of tons on Earth, and this incredible density means the heat is not just on the surface, it's locked into every centimeter of the star's interior. The particles are packed so tightly together that the normal processes for losing heat are completely dominated by new, exotic physics. The cooling process for a neutron star is a dramatic race against time, governed by two powerful and competing mechanisms. For the first several hundred to 1,000 years, the primary method of cooling is through neutrino emission. Neutrinos, those nearly massless ghost particles that barely interact with matter, are produced in vast quantities deep within the ultra-dense core. Because they so rarely collide with other particles, they can stream directly out from the center of the star, carrying away enormous amounts of energy without being slowed down. This makes for an incredibly efficient cooling system, causing the star's temperature to plummet rapidly during its early life. After this initial phase, the cooling rate slows significantly as photon emission. The release of heat as light from the surface takes over as the dominant process. This is a much slower way to lose energy, meaning it will take millions of years for a neutron star to cool down to temperatures we would consider merely extreme rather than astronomical. Adding another layer of complexity to this thermal tale is the neutron star's unbelievably powerful magnetic field. These fields are trillions of times stronger than Earth's, and they are not just a side feature, they actively shape how the star cools. In some cases, particularly with a class of neutron stars known as magnetars, these magnetic fields are so strong they can actually slow the cooling process. The field can create a rigid crust that acts as an insulating blanket, trapping heat within the star's interior for longer periods. In other regions, the magnetic field can funnel and focus the outflow of heat, creating hotspots on the surface that glow much brighter than the surrounding areas. This means the temperature isn't uniform. A neutron star can have scorching magnetic poles while its equator is significantly cooler, creating a thermal landscape unlike anything else in the universe. Even after 1,000,000 years of cooling, a neutron star's surface will still be far hotter than most main sequence stars, a lasting testament to the violent and energetic conditions of its birth. Yet even the mind-bending temperatures of a supernova and the lingering heat of a neutron star are not the final word on cosmic extremes. To find the most consistently powerful engines of heat in the universe, we must look to the very edge of observable reality, to the brilliant, beacon-like hearts of distant galaxies known as quasars. These are not single stars, but the incredibly active nuclei of galaxies, powered by the most terrifying gravitational traps imaginable, supermassive black holes. And it is within the swirling, doomed maelstrom of matter falling into these black holes that temperatures are sustained at a ferocious millions of degrees, creating an environment of such relentless energy that it can outshine 1,000 galaxies. The furnace of a quasar is not the black hole itself, but the colossal structure feeding it, an accretion disk. Imagine a whirlpool of cosmic proportions, a flat, spinning disk of gas, dust, and shredded stars spiraling inward at velocities approaching the speed of light. This isn't a gentle process, it's a violent, chaotic traffic jam on an unimaginable scale. As countless particles are pulled by the black hole's immense gravity, they don't fall straight in. Instead, they orbit at different speeds, with material closer to the center moving much faster than the material farther out. This difference in velocity creates a devastating friction, as particles and gas clouds constantly collide and rub against each other. These collisions transfer energy into motion and, crucially, into heat. It's the same principle as rubbing your hands together to warm them up, but amplified to a cosmic scale with trillions of tons of matter moving at relativistic speeds. The mechanical energy from this friction is so immense that it heats the entire accretion disk to temperatures ranging from hundreds of thousands to tens of millions of degrees Celsius. Compounding this frictional heating is another powerful force, compression. As matter is pulled inexorably inward, it is packed into an ever smaller volume, much like air in a bicycle pump gets hotter when you compress it quickly. In the accretion disk, the pressure becomes so intense that it superheats the material, helping to transform it into a fourth state of matter known as a plasma, a searing, electrically charged soup of atomic nuclei and free electrons. This combination of frictional heating and gravitational compression creates a sustained thermal engine of unbelievable power, converting the gravitational potential energy of infalling matter directly into raw, radiant heat. The process is so efficient that a significant fraction of the mass of the material is converted directly into energy, following Einstein's famous equation E equals mc2, far exceeding the efficiency of nuclear fusion that powers stars. Detecting and measuring these temperatures across billions of light years is one of astronomy's great triumphs. We can't send a probe; instead, scientists analyze the light these quasars emit. The accretion disk, glowing at millions of degrees, produces a tremendous amount of high-energy radiation, particularly in the ultraviolet and X-ray portions of the electromagnetic spectrum. By carefully dissecting the quasar's spectrum, the unique fingerprint of light spread out across different wavelengths, astronomers can identify the telltale signatures of specific elements within the hot plasma. The way these elements absorb and emit light changes dramatically with temperature, allowing researchers to work backwards and calculate the intense heat of their environment. The sheer brightness of a quasar, often outshining its entire host galaxy, provides a clear signal that points directly to the unimaginable energy being generated within its central engine, a perpetual inferno where gravity turns entire suns into light and heat. Lurking in the cosmic shadows between true stars and giant planets are the enigmatic brown dwarfs, often called failed stars because they occupy a mysterious mass gap that denies them a star's brilliant fate. These celestial objects form just like stars from the collapse of a gas cloud, but they simply didn't gather enough material to ignite the sustained nuclear fusion that defines a true star. Their mass is the key to their thermal identity, too large to be classified as a planet, yet too small to burn hydrogen in their cores. This places them in a unique thermal category all their own, with surface temperatures that can range from a relatively cool 300 degrees Celsius, hot enough to melt lead, up to a scorching 3000 degrees Celsius, which rivals the cooler red dwarf stars. The internal story of a brown dwarf is a fascinating tale of a fire that almost was. In their earliest youth, they do experience a brief period of fusion, but it's not the long-lasting hydrogen fusion that powers main sequence stars. Instead, their initial gravitational collapse provides enough heat and pressure to fuse deuterium, a heavier isotope of hydrogen also known as heavy hydrogen. This process is far less efficient than standard hydrogen fusion and depletes the available deuterium fuel relatively quickly, often within only a few million years, a mere blink in cosmic time. Some of the more massive brown dwarfs might also burn lithium for a short period. After this brief stellar flash in the pan, the nuclear processes cease. From that point on, a brown dwarf's life is a long, slow process of cooling and fading, its internal heat coming only from the slow release of the gravitational energy from its initial formation, with no new fusion energy to replenish what is radiated away into space. This unique origin story creates a thermal spectrum that is utterly different from anything else in the universe. Unlike stars, which maintain a relatively steady temperature for billions of years, and planets which are heated externally by their sun, a brown dwarf's temperature is its primary defining characteristic. Astronomers actually use temperature to classify them into spectral types. L dwarfs are the hottest, with temperatures up to 2000 degrees Celsius and atmospheres often containing clouds of molten iron and silicate rocks. As they cool further, they transition into the T dwarfs, often called methane dwarfs, because their atmospheres, now cooled to between about 600 and 1300 degrees Celsius, are cool enough for methane gas to form, giving them a distinct infrared signature. The coolest and oldest of the bunch are the Y dwarfs, with some discovered to have temperatures barely above that of a warm summer day on Earth, some even dipping below the 100-degree mark. Studying these failed stars provides incredible insight into the fine line that separates a planet from a star. Their atmospheres are complex laboratories, hosting weather patterns more violent than Jupiter's Great Red Spot, with clouds of liquid iron and rainstorms of molten minerals or hot sand. They represent a missing link, a third category of object that helps us understand the formation of both gas giant planets and the smallest stars. By measuring their temperatures and compositions, we can learn about the conditions present in the early solar system and better understand the variety of worlds that might exist in the vast spaces between the stars, hidden from visible light but glowing brightly with the telltale heat of their failed ambition. While the crushing gravity of Jupiter creates a furnace of friction on Io, another moon in our solar system presents a completely different thermal mystery, one hidden beneath a frozen crust. Saturn's enigmatic moon Enceladus, a gleaming white world barely 500 kilometers across, should be a frozen, geologically dead ice ball. Its surface is a pristine landscape of fresh, brilliant ice that reflects almost all sunlight, making it one of the most reflective objects in our solar system. With surface temperatures plunging to a bitter negative 200 degrees Celsius, it appears to be the epitome of a cold, inert celestial body. Yet, against all logic, this tiny moon is a world of astonishing geological activity, and the secret lies in a global ocean of liquid water hidden deep beneath its icy shell, warmed by a powerful and unexpected heat source. The first hints of this hidden warmth came from the Cassini spacecraft, which began orbiting Saturn in 2004. As it flew past Enceladus, its instruments detected something extraordinary: gigantic plumes of water vapor and ice crystals erupting from massive fractures near the Moon's south pole, shooting hundreds of kilometers into space. These weren't random geysers, they were evidence of a pressurized subsurface ocean, forcefully venting its contents into the vacuum. For liquid water to exist there, even under an insulating layer of ice, a significant source of internal heat was required to offset the intense cold of space. The surface temperature was deceptive. Deep below, Enceladus was anything but frozen solid. The engine powering this unexpected warmth isn't radioactive decay, as with Earth, or the fierce gravity of its parent planet, as with Io. Instead, Enceladus is heated by a subtle and continuous gravitational tug of war. As this small moon orbits Saturn, its path isn't a perfect circle, it's slightly elliptical. This means its distance from the giant planet is constantly changing. Saturn's immense gravity pulls more strongly on Enceladus when it's closer and less strongly when it's farther away. This varying gravitational force stretches and flexes the Moon's rigid core and icy shell in a process known as tidal heating. This constant flexing generates internal friction, much like repeatedly bending a metal coat hanger back and forth until it becomes hot to the touch. On a planetary scale, this friction produces enough consistent thermal energy to maintain a liquid saltwater ocean, perhaps dozens of kilometers deep, between the Moon's rocky core and its outer icy crust. This discovery transforms Enceladus from a simple ice moon into one of the most promising places in our entire solar system to look for evidence of life beyond Earth. The plumes Cassini sampled contained not just water vapor, but also an intriguing cocktail of organic molecules like methane, propane, and acetylene, along with tiny grains of silica minerals that on Earth typically form in hot water interacting with rock. This suggests that on the seafloor of Enceladus's dark ocean, hydrothermal vents may be actively spewing mineral-rich, superheated water into the environment. On our own planet, such vents, completely cut off from sunlight, are thriving oases of life, supporting complex ecosystems that draw their energy from chemistry rather than photosynthesis. The presence of liquid water, a source of heat, organic molecules, and a likely energy source creates an almost perfect checklist of ingredients needed for life as we know it. The extreme cold of its surface, therefore, acts as a protective lid over a potentially warm, watery, and habitable world, making Enceladus a stunning example of how a frigid exterior can hide a world of surprising and life-giving warmth. But what if we could push beyond even the coldest nebula and peer into the very background hum of the cosmos itself? This brings us to a temperature that is everywhere, a faint echo of creation that permeates every cubic centimeter of the universe. It's the temperature of deep space itself, a constant negative 270.45 degrees Celsius, just 2.7 degrees above absolute zero. This isn't the cold of a place, but the baseline temperature of the universe, and it comes from the most important fossil in all of cosmology, the cosmic microwave background radiation. This incredibly uniform chill is the faded afterglow of the Big Bang, the remnant heat from the universe's fiery birth nearly 13.8 billion years ago. In the earliest moments, the universe was an unimaginably dense and hot soup of particles and energy. As it expanded and cooled over hundreds of thousands of years, it reached a critical temperature threshold where electrons could finally combine with protons to form the first stable hydrogen atoms. This event, known as recombination, suddenly made the universe transparent. For the first time, light could travel freely across vast distances instead of constantly bouncing off free electrons. That first flash of light, released when the universe was a mere 300,000 years old, has been traveling ever since, stretched and cooled by the relentless expansion of the universe itself. What started as a blinding flash of visible light has been redshifted by the expansion of space over billions of years. Its wavelength stretched out until it now resides in the microwave portion of the electromagnetic spectrum. This is why we call it the cosmic microwave background. It's not radiation coming from specific stars or galaxies. It is the literal thermal energy of space-time, a snapshot of the infant universe imprinted across the entire sky. If you could see microwave radiation, the entire night sky would glow with a uniform, faint light, a testament to our universe's hot, dense beginning. The discovery of this background radiation in 1964 by Arno Penzias and Robert Wilson was arguably one of the most important scientific findings of the 20th century. They were using a large radio antenna and were plagued by a persistent, uniform static noise that came from every direction, regardless of where they pointed their instrument. After meticulously eliminating every possible source of interference, including famously cleaning out pigeon droppings from the antenna, they realized the noise was real and cosmological in origin. They had inadvertently stumbled upon the cooled remnant of the Big Bang itself, a discovery that earned them the Nobel Prize and provided the strongest evidence yet for the Big Bang theory, effectively ending the scientific debate between it and the rival steady-state model. The incredible uniformity of this radiation is what makes it so special. No matter where you look in the sky, the temperature is almost exactly the same, varying by less than 1/1000th of a degree. This near-perfect uniformity tells us that the early universe was an extremely smooth and homogeneous place. However, it is the tiny, tiny fluctuations in this temperature, the anisotropies, that are truly revolutionary. These minute variations, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, represent the primordial seeds of all structure in the universe. The slightly denser, slightly warmer spots in this ancient light are the gravitational wells that would, over billions of years, pull in enough matter to form the first galaxies, stars, and ultimately everything we see today. We are, in a very real sense, seeing the blueprint for the cosmic web imprinted in the faint, cold glow of the universe's first light. These mind-bending temperatures aren't achieved in massive stellar furnaces or cosmic explosions, but within the precisely controlled confines of a laboratory here on Earth. At facilities like the relativistic heavy ion collider at Brookhaven National Laboratory in New York, scientists have created the hottest human-made temperatures in history, briefly generating a searing plasma at over 4 trillion degrees Celsius. To put that almost incomprehensible number into perspective, it is more than 250,000 times hotter than the core of our Sun, a thermal spike so intense that it, for a fleeting instant, vaporizes the very structure of matter itself. This isn't just about setting a record, it's a deliberate attempt to turn back the cosmic clock and recreate the conditions that existed a mere fraction of a second after the Big Bang. The process of generating these temperatures is a masterpiece of precision engineering and fundamental physics. Scientists don't use traditional heating methods like lasers or furnaces. They instead use the immense energy of motion. They take the nuclei of heavy atoms like gold or lead and strip them of their electrons. These positively charged ions are then fed into a massive circular accelerator, a ring over 2 miles in circumference, where powerful superconducting magnets whip them to over 99.99% of the speed of light. At these relativistic velocities, the ions carry a phenomenal amount of kinetic energy. The experiment culminates when 2 beams of these ions, traveling in opposite directions, are steered into a head-on collision. The energy of their motion is instantaneously converted into an unimaginable concentration of heat and density at the point of impact, creating a fireball no larger than a single atomic nucleus, but with a temperature measured in trillions of degrees. Within this microscopic inferno, something extraordinary happens to matter. The protons and neutrons that make up the atomic nuclei are themselves torn apart under the extreme energy. These particles are normally held together by the strong nuclear force, which is mediated by particles called gluons, but at 4 trillion degrees that force is overcome. The colliding energy is so great that it melts the protons and neutrons into their most fundamental building blocks, a soup of free quarks and gluons. This exotic state of matter is known as quark-gluon plasma, and it is believed to be the state that filled the entire universe in the first few millionths of a second after its birth, before it expanded and cooled enough for quarks and gluons to combine and form the stable particles we know today. By creating and studying this plasma, physicists are essentially performing cosmic archaeology, probing the properties of the infant universe in a laboratory setting. The most astonishing aspect of this quark-gluon plasma is not just its temperature, but its behavior. Theoretical physicists initially predicted it would behave like a gas, but the data from these collisions revealed something completely unexpected. It acts like a perfect, frictionless liquid. This means it has extremely low viscosity, allowing it to flow with virtually no resistance. This discovery was a major surprise that forced a revision of our models for the early universe's behavior. The ability to create and analyze this primordial soup, even for the tiniest fraction of a second, allows scientists to test the fundamental theory of the strong force, known as quantum chromodynamics, under the most extreme conditions possible. Each collision is like creating a new micro-universe, providing a unique window into the forces that shaped everything we see around us, and deepening our understanding of how the cosmos evolved from a superheated primordial state into the structured universe of atoms, stars, and galaxies we inhabit today. Now, stepping away from the fiery beginnings of the universe, we encounter the ultimate fate of most stars, including our own sun, a fate not of explosive demise, but of a long, slow, and incredibly precise cosmic cooling. These are white dwarf stars, the exposed super-dense cores of dead stars, and they serve as some of the most reliable and fascinating thermometers in the entire cosmos. A newly formed white dwarf is a blistering ember with surface temperatures soaring above 100,000 degrees Celsius, shining with a brilliant white-hot light. But this intense heat is not sustained by any internal fire. It is merely the residual warmth from the star's earlier life, and it has nowhere to go but out into the cold of space, beginning a cooling process so slow and predictable that it allows us to literally read the age of the universe from its fading glow. White dwarfs are the final evolutionary state for the vast majority of stars, those not massive enough to end their lives in a supernova. Once a star like our Sun exhausts its nuclear fuel, it expels its outer layers in a beautiful planetary nebula, leaving behind only its incredibly dense core. This core, typically composed of carbon and oxygen, is no longer generating energy through fusion. It is supported against its own immense gravity not by thermal pressure, but by a quantum mechanical effect known as electron degeneracy pressure, a force that arises because the electrons are packed together as tightly as the laws of physics will allow. A white dwarf packs a mass comparable to our Sun into a volume no larger than Earth, making a single teaspoon of its material weigh several tons. With no new energy being created, the white dwarf's only option is to radiate its stored heat away over an almost unimaginable timescale, following a very specific and well-understood cooling curve. This process of cooling is what makes them such valuable cosmic tools. Initially, the white dwarf is so hot that it shines brightly in visible and ultraviolet light. As it cools, its color shifts from white to yellow, then to orange, and eventually to a dim red. The rate at which this happens is not a guess. It is governed by the physics of its dense, crystalline interior. The heat from the interior must travel through a mantle that is slowly crystallizing, starting from the core outward, and then through a thin atmosphere of hydrogen or helium before it can finally radiate into space. The entire sequence is remarkably orderly and predictable, almost like watching a hot piece of iron cool down at a fixed, calculable rate, only slowed down to a billion-year timescale. Astronomers have used this predictable cooling to create sophisticated models known as white dwarf cooling curves. By observing the temperature and brightness of the faintest, coolest white dwarfs in a star cluster, scientists can determine precisely how long those stars have been cooling. Since all the stars in a given cluster were born at roughly the same time, the coolest white dwarfs provide a direct lower limit for the cluster's age. This method has been instrumental in dating some of the oldest star clusters in our galaxy, providing a crucial cross-check for other estimates of the universe's age. The very coolest white dwarfs we can observe have been slowly radiating their heat for over 10 billion years, acting as silent, ticking chronometers that have been counting down since not long after the Milky Way itself first formed. The ultimate end of this journey is a theoretical object known as a black dwarf, a white dwarf that has radiated away all of its residual heat and faded to the background temperature of the universe. It would be a cold, dark sphere of crystallized carbon and oxygen, invisible against the blackness of space. The profound significance is that our universe is not yet old enough for even the first white dwarfs to have reached this final state. The trillions of years required for a white dwarf to cool completely is far longer than the current age of the universe, which is a little under 14 billion years. This means that every white dwarf we observe, no matter how dim, is still on its long journey toward absolute cold, a silent testament to the fact that our cosmos, for all its ancient grandeur, is still far too young to have seen the final chapter in the life cycle of its most common stars. This brings us to a profound cosmic irony. The birthplaces of stars, the very furnaces of the universe, are among the coldest natural regions known to exist. Deep within the dark, swirling hearts of molecular clouds, where new stars and planetary systems are forged, temperatures routinely plunge to a mere 10 to 20 degrees above absolute zero, around -260 degrees Celsius. These are not the empty voids between galaxies, but dense, rich clouds of gas and dust, and their extreme cold is the essential ingredient that makes the miracle of star formation possible in the first place. The reason for this deep chill is a simple matter of shielding. A giant molecular cloud is a vast cosmic nursery, often light years across and containing enough mass to form thousands of stars like our Sun. Its outer layers are peppered with dust grains, tiny particles of silicon, carbon, and iron. These minuscule specks are the universe's ultimate sunshade. They are incredibly effective at blocking out the faint starlight and background radiation that permeates interstellar space, creating dark, shadowed interiors where the ambient warmth of the galaxy cannot penetrate. Without an internal heat source, the core of the cloud simply radiates its own tiny amount of thermal energy out into the void, cooling down to these cryogenic temperatures. It is within this frigid, dark sanctuary that the delicate and necessary work of building a star can begin. The key player in this process is molecular hydrogen, or H2. In the warmer, more exposed regions of space, hydrogen exists primarily as individual atoms. But for a cloud to collapse and form a star, it needs to be much denser, and individual atoms are notoriously bad at clumping together. They tend to just bounce off one another. The extreme cold changes everything. At these temperatures, atoms and molecules are moving incredibly slowly. When a hydrogen atom drifts and sticks to the surface of a cold dust grain, it doesn't have enough energy to bounce right back off. It lingers, shivering on the surface, just long enough for another hydrogen atom to arrive and form a partnership. The dust grain acts as a matchmaker and a catalyst, providing a solid, cold surface where two hydrogen atoms can meet, bond, and form a stable hydrogen molecule. This process, known as surface catalysis, is how the vast majority of molecular hydrogen in the universe is created, and it only works efficiently in the deep freeze of a molecular cloud's heart. Once a significant amount of molecular hydrogen has formed, the stage is set for collapse. Hydrogen molecules are far more effective at cooling the cloud than individual atoms. As the cloud contracts very slowly under its own gravity, the molecules can radiate away the tiny amounts of heat generated by the compression through faint rotational and vibrational emissions. This efficient cooling is the cloud's pressure release valve. It prevents the internal heat from building up and counteracting the inward pull of gravity. The cold, therefore, acts as a gravitational amplifier. It allows the cloud to continue condensing, fragmenting into smaller and denser knots called protostellar cores. Each of these cores, still at a temperature of just a few tens of degrees above absolute zero, continues to fall inward upon itself, growing denser and denser until the pressure and temperature at its center become so unimaginably high that nuclear fusion finally ignites and a new star flares to life. So the next time you look up at the night sky and see the brilliant points of light, remember this incredible thermal paradox. The hottest objects in the universe, stars that burn at millions of degrees, are born from the coldest possible places, from dark, silent clouds where the cold is not an absence of life, but a necessary creative force that patiently gathers the raw material of creation. But getting back to Earth from the cold silence of space presents its own thermal nightmare, a harrowing trial by fire that every returning spacecraft must survive. This is the phenomenon of atmospheric re-entry, where a vehicle can experience temperatures soaring to a blistering 1,650 degrees Celsius, hot enough to melt steel and vaporize most known materials. This isn't simply friction from moving fast through air like a meteor streaking across the sky. It's a far more complex and violent process driven by one of physics' most powerful forces, compression. As a spacecraft like a returning capsule streaks back toward Earth, it's traveling at orbital velocities around 28,000 kilometers per hour. It slams into the upper atmosphere, which, while incredibly thin, is still populated with molecules of gas. The spacecraft is moving so phenomenally fast that it doesn't have time to gently push these molecules aside. Instead, it plows into them, compressing the air directly in front of it into an incredibly dense, superheated pocket of plasma. Imagine a piston in a diesel engine compressing air to make it hot enough to ignite fuel, but on a massive scale and at hypersonic speeds. The spacecraft essentially carries a massive cushion of searing hot gas ahead of it, a protective yet terrifying bubble of energy that absorbs the immense thermal load, preventing the vehicle's surface from making direct contact with the hypersonic airstream. The kinetic energy of the spacecraft's motion is thus converted directly into thermal energy within this compressed gas layer, creating a brilliant fireball that envelops the vehicle. Surviving this inferno requires one of engineering's most ingenious solutions, the ablative heat shield. Unlike a simple insulator that just tries to block heat, an ablator is designed to sacrifice itself in a carefully controlled manner to protect the vehicle within. The shield is typically made from a special resinous material embedded with high-strength fibers and contains countless tiny pores. As the plasma heats the shield's outer surface to thousands of degrees, the material doesn't just get hot. It undergoes a complex series of chemical and physical transformations. The outer layer intentionally chars, melts, and vaporizes, a process called ablation. This phase change is crucial because it consumes a tremendous amount of energy. The heat is used to break down the material's chemical bonds and turn it into gas rather than being conducted inward to the spacecraft's hull. Meanwhile, the vaporizing material is blown off the surface, injecting cooler gas into the superhot plasma layer and effectively thickening the protective boundary, a bit like a sweat cooling your skin through evaporation. This entire dramatic process is a carefully orchestrated trade. The vehicle sacrifices a precisely calculated mass of its heat shield to safely dissipate the apocalyptic levels of heat generated during those few minutes of peak heating. Mission controllers on the ground monitor the temperature and ablation rates, knowing that the shield is quite literally giving its life for the mission. By the time the spacecraft has slowed to subsonic speeds and the fireball subsides, the heat shield is left scarred and charred, a testament to the brutal journey it has endured. Every successful landing, from the Mercury and Apollo capsules to today's SpaceX Dragon and Orion spacecraft, is a direct result of our deep understanding of this extreme physics, turning a potentially vaporizing return into a controlled and survivable descent through a man-made hell. While our star may seem like a uniform ball of fire from a distance, its surface is actually a dynamic tapestry of light and shadow, home to some of the most dramatic and visually striking temperature variations in our solar system. These are sunspots, the planet-sized blemishes that dot the photosphere, and they represent a fascinating thermal paradox. A typical sunspot appears dark because its center, called the umbra, registers at around 3,000 to 4,000 degrees Celsius. That's still scorching hot by any earthly standard, yet it's significantly cooler than the surrounding photosphere, which blazes at a steady 5,500 degrees. This 1,500 to 2,000 degree difference is why they appear so dark in contrast. They're simply emitting less light, creating the illusion of a hole or a spot on the sun's brilliant face. The engine behind these massive cool spots isn't a lack of energy, but rather a powerful magnetic obstacle. Sunspots are essentially the visible footprints of intense, concentrated magnetic fields bursting through the sun's visible surface. The sun's interior is a churning plasma, and in its outer layer, the convective zone, hot gas constantly rises from the interior, cools at the surface, and then sinks back down in a continuous cycle that efficiently transports heat. This process is the sun's primary heating mechanism for its surface. However, when a powerful magnetic field loop erupts through the photosphere, it creates a massive kink that acts as a rigid barrier, powerfully suppressing this churning convective motion. The magnetic field is so strong that it prevents the hotter plasma from below from rising to the surface within the sunspot's boundaries. With this natural heat delivery system stifled, the region within the magnetic loop cools down considerably, creating the sunspot we observe. These magnetic monsters are not static features. They are born, evolve, and vanish in a rhythm that dictates the sun's entire personality. Sunspots rarely appear alone. They usually form in groups with complex magnetic arrangements, and their numbers rise and fall in a remarkably regular 11-year cycle known as the solar cycle. At solar minimum, the sun's face can be completely clear for weeks on end. As the cycle progresses toward solar maximum, the magnetic field within the sun becomes increasingly tangled and complex, leading to more and more sunspots breaking through the surface. This peak activity is marked by a frenzied appearance, with dozens of spots and clusters visible at any one time. This cycle is the heartbeat of solar activity, governing the frequency of solar flares and coronal mass ejections, which are themselves directly triggered by the complex magnetic interactions in and around these sunspot groups. Studying these cooler blemishes has given us profound insight into the sun's inner workings and its influence on our planet. By tracking the number and location of sunspots over centuries, astronomers have not only identified the 11-year cycle, but also discovered much longer periods of unusual activity, such as the Maunder minimum in the 17th century, when sunspots virtually disappeared for decades, coinciding with a period of exceptionally cold winters on Earth known as the Little Ice Age. This historical link provides a compelling, though complex, connection between solar magnetism, as evidenced by sunspots, and Earth's climate. Today, continuous monitoring of sunspots helps space weather forecasters predict solar storms, those bursts of radiation and charged particles that can disrupt satellites, power grids, and communications. making the study of these cooler spots a critical part of protecting our modern technological world. Moving out from the protective cocoons of molecular clouds, we enter the vast and largely empty expanses between the stars, a region known as the interstellar medium. It's a common misconception that this space is a complete and uniform vacuum. In reality, it's a dynamic and complex ecosystem of matter and energy, and it exhibits one of the most astonishingly wide temperature ranges found anywhere in nature. This tenuous material can be as cold as the darkest molecular cloud, hovering around -270 degrees Celsius, or it can be superheated to millions of degrees in vast, expanding bubbles of plasma. This incredible thermal diversity isn't random chaos. It's a direct consequence of the life and death cycles of the stars themselves, a story written in hot and cold gas across the galaxy. The coldest regions of the interstellar medium are the ones we've already explored, the dense, dark molecular clouds. Their chilling efficiency comes from their dust content, which blocks external starlight and allows internal heat to radiate away into space, and from molecular hydrogen, which provides a highly effective cooling mechanism. These clouds are the cold storage units of the galaxy, the deep freezes where the raw material for future generations of stars and planets is kept on ice, waiting for the gravitational trigger to begin the process of stellar birth. The searingly hot end of this spectrum is created by the most massive and energetic stars. Imagine a brilliant, massive O-type star, blazing with such intensity that it floods its surroundings not just with light, but with a torrent of charged particles streaming from its surface at supersonic speeds. This is a stellar wind, but on a scale that makes the solar wind from our sun seem like a gentle breeze. This relentless outflow carves out a gigantic cavity in the surrounding interstellar gas, compressing and shocking the material at its edge and heating it to temperatures of tens of thousands of degrees. This creates what astronomers call an H-II region, a glowing bubble of ionized hydrogen that announces the presence of a powerful young star. But the true thermal extremes are reached when these massive stars meet their end. A supernova explosion does more than just create elements. It unleashes a shockwave of unbelievable force that blasts outward at thousands of kilometers per second. This expanding sphere of energy sweeps up the surrounding interstellar material, whether it's cold cloud gas or the warmed gas of an H-II region, and violently compresses and heats it. The shockwave acts like a cosmic snowplow, piling up a dense, bright shell of cool gas at its outer edge, while the interior of the bubble is filled with a superheated, incredibly thin plasma that can reach temperatures of 10 million degrees Celsius or more. These structures, known as supernova remnants, are the primary engines that heat the interstellar medium to its highest temperatures, and they can persist for tens of thousands of years, slowly expanding and mixing their scorching contents with the cooler material around them. Over millions of years, the combined effect of countless stellar winds and supernova, particularly from stars that form in clusters, can merge these individual bubbles into a single, colossal structure known as a superbubble. These can be hundreds of light years across, dominating the structure of a galaxy's spiral arms. Within a superbubble, the temperature is a complex tapestry. The interior is filled with the combined, diluted plasma from all the contributing events, still sitting at millions of degrees. The walls of the bubble are a turbulent mix of shocked, compressed, and heated gas from the original interstellar medium, while scattered throughout this vast volume can be tiny, surviving fragments of the original cold molecular clouds that somehow avoided being completely evaporated by the onslaught. This creates an environment where temperatures can vary by a factor of 100,000 across relatively short distances, a testament to the powerful and opposing forces of stellar creation and destruction that continuously reshape and reheat the material between the stars. These thermal currents rising from the deepest parts of our planet bring us to the spectacular and violent expressions of Earth's internal heat known as mantle plumes. Far below the tectonic plates that form our planet's mobile surface, originating from a mysterious zone near the core mantle boundary nearly 3,000 kilometers down, these colossal upwellings of superheated rock represent some of the most powerful thermal anomalies on Earth. A mantle plume is essentially a planetary-scale heat pipe, a conduit of solid yet ductile rock that slowly rises from the deepest mantle because it is significantly hotter and therefore less dense than the surrounding material. At their source, these plumes can reach temperatures around 1,400 degrees Celsius, hundreds of degrees hotter than the ambient mantle rock they surge through, giving them the buoyancy to journey upward over millions of years. The journey of a mantle plume is a testament to the slow but unstoppable power of heat-driven motion. It begins its ascent as a vast, bulbous head that can be hundreds of kilometers across, followed by a narrower, sustained tail that continues to feed hot material from the deep. As this enormous blob of rock ascends, the immense pressure upon it decreases, allowing the rock, though still solid, to behave like a viscous fluid and undergo decompression melting. A small percentage of the rock actually melts into magma long before it reaches the surface. This molten rock, being less dense than the solid mantle, then continues to percolate upward with even greater urgency, eventually pooling in massive chambers in the crust and creating the fuel for some of the most dramatic volcanism on the planet. This process is fundamentally different from the volcanism that occurs at plate boundaries. It is a direct pipeline of heat from the very edge of Earth's core, punching straight through the mantle and crust without regard for the tectonic drama unfolding above it. The most famous and visually stunning result of this process is hotspot volcanism, and the Hawaiian Emperor Seamount Chain is the textbook example. Here, the Pacific tectonic plate has been slowly drifting northwestward for over 80 million years, moving at about the same speed your fingernails grow. But beneath it, a stationary mantle plume has been continuously burning a hole through the crust like a welder's torch held against a moving sheet of steel. As the plate moves, the plume creates a series of volcanoes, each one active for a few million years before the plate carries it away from the heat source, cutting it off and extinguishing it. The island of Hawaii, with its active volcanoes of Kilauea and Mauna Loa, is currently directly over this plume, which is why it is the largest and most volcanically active island in the chain. To the northwest, the islands become progressively older, smaller, and more eroded, trailing all the way to the ancient submerged seamounts that eventually curve north into the Emperor Chain, creating a visible record of both the plate's direction of motion and a change in its path roughly 47 million years ago. Perhaps the most awe-inspiring manifestation of a mantle plume on a continent is the Yellowstone hotspot. Here, the plume has interacted with the thick North American continent, resulting in a history of catastrophic supervolcanic eruptions rather than the gentle shield volcanoes of Hawaii. Over the past 17 million years, the North American plate has been moving southwest over this stationary plume, leaving a scar of volcanic calderas across the Snake River Plain in Idaho. Each of these calderas marks the location of a colossal eruption that occurred when the continent was directly above the plume. Today, the hotspot sits beneath Yellowstone National Park, fueling its famous geysers and hot springs with immense geothermal energy. The magma chamber beneath Yellowstone is one of the largest on Earth, a reminder of the planet-altering power that lies dormant, sustained by a direct connection to the searing heat of the deep mantle. These plumes are not merely geological curiosities, they are primary drivers of plate tectonics itself. Their upwelling movement helps to organize the larger-scale convection currents in the mantle that push and pull the tectonic plates, contributing to the continuous renewal of Earth's surface and playing a crucial role in the long-term cycling of heat from our planet's fiery interior. But even the terrifying heat of a supernova pales before the most violent and energetic explosions in the modern universe, events so powerful they can outshine entire galaxies in a flash of light. These are gamma-ray bursts, the universe's ultimate cosmic detonations, and within their relativistic jets, temperatures are thought to reach an almost nonsensical 1 trillion degrees Celsius. To even begin to comprehend this number, consider that it is over 60 times hotter than the core of a supernova, and, for a fleeting moment, creates temperatures not seen since the first seconds after the Big Bang itself. These are not mere stellar explosions, they are the birth cries of black holes or the death rattles of the most massive stars. Events that release more energy in 10 seconds than our Sun will emit across its entire 10 billion-year lifespan. These bursts fall into two primary categories, each with its own apocalyptic origin story. The long-duration bursts, lasting more than 2 seconds, are believed to be the result of a special type of supernova often called a collapsar. When a truly massive, rapidly spinning star collapses, it doesn't just explode outward, its core implodes directly into a black hole. The remaining stellar material forms a vast, swirling accretion disk around this newborn singularity, and along the star's rotational axis, where centrifugal forces are strongest, the incredible pressure and magnetic fields can funnel material into a pair of tightly focused jets. These jets blast outward at over 99.99% of the speed of light, punching through the outer layers of the dying star before screaming out into interstellar space. It is within these narrow, ultra-relativistic jets that the conditions for a trillion-degree plasma are created. The short-duration bursts, lasting less than 2 seconds, are thought to originate from the collision of two ultra-dense stellar remnants like neutron stars. When these incredibly massive objects spiral into each other and merge, they too can form a black hole surrounded by a torus of neutron-rich material, launching a similar pair of blisteringly hot jets into the cosmos. We cannot, of course, stick a thermometer into a gamma-ray burst occurring billions of light-years away. So how do we possibly measure such an unimaginable temperature? The answer lies in the unique fingerprint of light the burst emits, its radiation spectrum. As the material in the jet is accelerated to near light speeds, it becomes a soup of electrons, positrons, and photons trapped within the magnetic fields of the jet. The photons constantly collide with the high-energy electrons in a process called inverse Compton scattering, where the photons gain a tremendous amount of energy from the electrons. This process transforms the radiation into the extremely high-energy gamma rays that give these events their name. The key to unlocking the temperature is in the distribution of these gamma-ray energies. The spectrum of a gamma-ray burst isn't smooth, it shows a distinct peak at a certain energy level. The position of this peak is directly related to the temperature of the plasma within the jet. By meticulously analyzing this spectral peak from data gathered by space telescopes like NASA, a Fermi Gamma-Ray Space Telescope, and the Neil Gehrels Swift Observatory, astrophysicists can work backwards through the complex physics of relativistic plasmas to calculate the incredible thermal energy that must have been present to produce it. The detection of these events is a global effort, with a network of satellites constantly monitoring the sky for the telltale flash of high-energy photons. When a burst is detected, its coordinates are instantly relayed to observatories around the world, which swivel to capture the fading afterglow in visible light, X-rays, and radio waves. This multi-wavelength follow-up is crucial, as it helps pin down the burst's distance and host galaxy, confirming that we are witnessing events from the far reaches of the cosmos. The temperature calculation is a triumph of theoretical astrophysics, combining Einstein's theory of special relativity with quantum mechanics and plasma physics. It demonstrates that even for the most extreme phenomena, the universe leaves behind a measurable signature, a cosmic barcode that we can learn to read, allowing us to comprehend the incomprehensible and measure the temperature of a fireball from the edge of time and space. And just when you think you've seen every form of volcanic activity the universe has to offer, the ice worlds of our outer solar system present a bizarre and beautiful twist. Forget fiery rivers of molten rock, Imagine instead a volcano that erupts a slow-moving, slushy slurry of water ice, methane, and ammonia into a sky hundreds of degrees below freezing. This is cryovolcanism or cold volcanism, and it's a geological process that redefines our understanding of what it means for a world to be alive. On frigid moons like Saturn's Enceladus and Neptune's Triton, the internal heat isn't strong enough to melt silicate rock into lava. Instead, it works its magic on a different set of materials, creating spectacular geysers of ice crystals that erupt from a subsurface ocean, painting the surface in brilliant white and leaving scientists in awe of the clever ways nature finds to stay active in the deep freeze. The driving force behind this icy spectacle is often tidal heating, a powerful and relentless gravitational engine. A moon orbiting a gas giant planet doesn't follow a perfectly circular path. Its orbit is usually slightly elliptical. This means its distance from the planet is constantly changing. The planet's immense gravity pulls more strongly on the moon when it's closer and less strongly when it's farther away. This varying gravitational pull stretches and flexes the moon's interior, generating internal friction and heat through constant deformation. It's the same principle as repeatedly bending a metal paperclip until it becomes hot to the touch, but on a planetary scale. This process is exceptionally efficient on moons like Enceladus, which is locked in an orbital resonance with another moon, Dione. This gravitational tug of war keeps Enceladus's orbit just eccentric enough to maintain this constant, life-giving flexing, preventing its interior from solidifying completely despite the cold of space. But heat alone isn't enough to explain the eruption of liquids at temperatures that would instantly flash freeze on Earth's surface. This is where the chemistry of these alien worlds becomes absolutely critical. The subsurface oceans on these moons aren't pure water. They're a complex brine, rich in dissolved compounds like ammonia and salts that act as a potent natural antifreeze. Ammonia, in particular, is remarkably effective at lowering the freezing point of water. On Earth, we use ethylene glycol in car radiators to prevent the coolant from freezing. On these distant moons, ammonia and salts perform the same function on a global scale. A mixture of water and ammonia can remain liquid at temperatures as low as -100 degrees Celsius, allowing vast liquid oceans to exist beneath ice shells that are themselves hundreds of kilometers thick. This antifreeze effect is what allows geological activity to persist in an environment of unimaginable cold. The eruption itself is a breathtaking sight. On Enceladus, fractures known as tiger stripes near its south pole act as nozzles for enormous geysers. The internal heat and pressure from the tidally warmed ocean force this liquid brine up through these cracks in the icy crust. As this supercooled mixture is exposed to the near vacuum of space, the water instantly flash freezes into a mist of tiny ice crystals, while trapped gases and volatile compounds like methane expand rapidly, launching the plume hundreds of kilometers into space. The Cassini spacecraft famously flew directly through these plumes, tasting their composition and discovering they contained organic molecules, salts, and silica nanoparticles, strong evidence for hydrothermal vents on the seafloor interacting with the rocky core. This makes cryovolcanism far more than a geological curiosity. It's the primary mechanism that transports the potentially life-hosting ingredients of a hidden ocean out into space where we can detect them. Neptune's largest moon, Triton, presents an even more alien version of this phenomenon. Voyager 2 images revealed dark, dusty geysers erupting from its nitrogen ice surface, staining the terrain below. Scientists believe sunlight penetrates Triton's transparent surface ice, warming a layer of darker, trapped nitrogen gas underneath. This gas builds up pressure until it finally bursts through the frozen crust, erupting in a violent plume that carries dark dust and ice particles high into the thin atmosphere. This makes Triton's cryovolcanism primarily driven by solar heating and sublimation, a different engine than the tidal heating on Enceladus, yet producing a similarly stunning result. The existence of such activity on a world so far from the Sun, where average temperatures hover around -235 degrees Celsius, proves that geological ingenuity knows no bounds. Cryovolcanism transforms these distant, icy moons from static snowballs into dynamic, evolving worlds, each with its own unique method of turning the deep cold into a source of spectacular and revealing activity. But if you truly want to witness a cosmic thermal carnival, a place where the full spectrum of temperature extremes exists simultaneously in a chaotic and beautiful dance, you need to look at one of the universe's most dynamic structures, a pulsar wind nebula. The most famous of these is the Crab Nebula, the spectacular remnant of a supernova observed by astronomers on Earth in the year 1054. Within its swirling, filamentary grasp, temperatures range from the profound cold of near absolute zero dust grains to the searing, relativistic heat of particles moving at nearly the speed of light, a range spanning over 1 billion degrees. This isn't a uniform environment, it's a multi-layered thermal engine, and its power source is the rapidly spinning neutron star at its very heart, the Crab Pulsar. This stellar cinder is the dynamo that brings the entire nebula to life. The Crab Pulsar rotates an astonishing 30 times every second, and with each rotation, its unimaginably powerful magnetic field, trillions of times stronger than Earth's, whips around like a cosmic lighthouse beam. This rapid spin, combined with the intense magnetic field, acts as a gigantic electric generator, creating incredibly strong electric fields around the star's magnetic poles. These fields are so potent that they rip charged particles' electrons and their positively charged counterparts, positrons, right off the neutron star's surface and accelerate them to velocities approaching the speed of light. This creates a relentless supersonic gale of high-energy particles streaming away from the pulsar, a phenomenon aptly named the pulsar wind. It is this wind that carves out and energizes the entire nebula. The particles in this wind are moving so fast that they possess a tremendous amount of kinetic energy, but the nebula itself is still filled with the slower-moving, expanding gas from the original supernova explosion. When the ultra-fast pulsar wind slams into this slower-moving shell of supernova debris, it creates a massive reverse shock wave. Think of it like a high-speed fire hose blasting into a placid pond. The point of impact is one of immense violence and energy transfer. It is at this shock front that the true thermal magic happens. The incoming particles are suddenly decelerated, and their colossal kinetic energy is efficiently converted into heat and radiation, superheating the gas at the shock boundary to temperatures of millions of degrees and causing it to glow brilliantly in X-rays, which we can observe with space-based telescopes. Yet the thermal story doesn't end at this hot shock front. As the energized particles diffuse outward from this boundary, they slowly lose their energy, emitting light across the entire electromagnetic spectrum as they go, from high-energy gamma rays down to radio waves. This creates the beautiful, glowing cloud of plasma we see in visible light images, but scattered throughout this hot plasma are much colder, solid particles, dust grains that either survived the supernova blast or condensed from the heavy elements forged within it. These tiny specks are shielded within the filaments of cooler gas and are only a few tens of degrees above absolute zero. This means that within the span of a single light year, you can have a cold dust grain chilling at -260 degrees Celsius just a short distance from a stream of electrons so energetic they are effectively at a temperature of billions of degrees. This coexistence of the ultra-hot and the ultra-cold is what makes these nebulae such fascinating thermal laboratories, showcasing the full, breathtaking range of physical conditions that can emerge from the corpse of a single dead star. Now, having explored the violent thermal extremes of stellar explosions and the delicate cold of interstellar clouds, we encounter a more subtle but equally fascinating atmospheric phenomenon that turns our basic expectations upside down. We're taught a simple rule of thumb: the higher you go, the colder it gets. Mountain peaks are snow-capped while valleys are warm. But this isn't a universal law. It's a frequent pattern in the lowest layer of an atmosphere, and nature is full of exceptions. Some of the most stable and important atmospheric regions on planets actually operate on a completely opposite principle, creating a thermal profile known as a temperature inversion, where the air gets warmer as you ascend. The most accessible example is right here above us in Earth's own stratosphere. If you were to ascend through our atmosphere in a balloon, you'd first pass through the troposphere, where temperature reliably drops with altitude. This is the realm of weather where convection currents constantly mix the air, but at a boundary called the tropopause, roughly 12 kilometers up, that trend completely reverses. Entering the stratosphere, the temperature begins to steadily increase, climbing all the way up to its outer limit about 50 kilometers above the surface. This inversion creates an incredibly stable layer, effectively acting as a lid that traps the churning weather of the troposphere below and giving the stratosphere its name, derived from the word for layered. The engine behind this inversion isn't the sun's direct heat, but a remarkable chemical process happening within the air itself. The stratosphere is home to the ozone layer, a concentration of ozone molecules, each made of 3 oxygen atoms. These ozone molecules are incredibly efficient at absorbing the sun's high-energy ultraviolet radiation. When a UV photon strikes an ozone molecule, the energy is converted into kinetic energy. The molecule vibrates and moves faster. Since temperature is just a measure of molecular motion, this absorption directly heats the surrounding air. The higher you go in the stratosphere, the more intense the ultraviolet radiation is, and the more ozone molecules are present to absorb it. This creates a perfect positive feedback loop for heating. Higher altitude means more UV absorption, which means more molecular motion, which means a higher temperature. This self-heating mechanism makes the stratosphere exceptionally stable, as the warmer air sitting on top of the cooler air below prevents the large-scale vertical mixing we see in the troposphere, which is why jets often fly in the lower stratosphere to find smoother, less turbulent air. Venus presents an even more dramatic and complex example of atmospheric inversion, but for entirely different reasons. The Venusian atmosphere is a suffocating blanket of carbon dioxide, and its thermal structure is a story of intense heating from above and below. Its surface is a scorching 465 degrees Celsius, heated by a runaway greenhouse effect. One might expect it to cool with altitude from that inferno, and it does, but only for the first 60 kilometers or so. Then, in a region between about 60 and 100 kilometers above the surface, the temperature stops dropping and begins to increase again, creating a massive inversion layer in the Venusian mesosphere. The cause here isn't ozone, but another potent absorber of solar energy, a mysterious, unknown ultraviolet absorber. Observations of Venus show dark patches in ultraviolet images that rotate around the planet, but scientists have not yet definitively identified the chemical compound responsible. This unknown substance, possibly a compound of sulfur or chlorine, is incredibly effective at soaking up solar energy, particularly in the UV spectrum. Much like ozone on Earth, this absorption process heats the upper atmosphere of Venus, creating the inversion. This layer acts as a crucial thermal barrier in the Venusian atmosphere. Interestingly, above this warm layer, the temperature once again plummets dramatically in the thermosphere. On Earth, our thermosphere is exceptionally hot due to absorption of extreme UV radiation. On Venus, however, the same unknown UV absorber that heats the mesosphere effectively acts as a sun shield, blocking most of the high-energy radiation from reaching the higher altitudes and leaving the Venusian thermosphere surprisingly cold. a fascinating paradox that highlights how different chemical processes can sculpt a planet's atmospheric temperature in counterintuitive ways. These inversions are far more than mere meteorological curiosities. They play a critical role in shaping a planet's climate and chemistry. The stability of an inversion layer acts as a physical barrier, effectively trapping aerosols, pollutants, and water vapor beneath it. On Earth, this is why we see the flat, anvil-shaped tops of cumulonimbus thunderclouds. They have hit the ceiling of the troposphere and cannot rise further into the stable, inverted stratosphere. This trapping effect also concentrates materials. On Venus, the main cloud deck of sulfuric acid droplets exists within and just below its inversion layer. Furthermore, the lack of vertical mixing in these stable layers means that chemicals can have very long residence times, allowing complex photochemical reactions to occur that wouldn't be possible in a more turbulent environment. The study of THESE Chinese letter thermal profiles provides a key to understanding not just weather, but the long-term evolution and chemistry of entire planetary atmospheres, revealing the delicate and often invisible processes that maintain the balance between a world's surface and the cold vacuum of space. Yet for all their raw power, the most extreme temperatures in the universe are often fleeting, lasting mere fractions of a second. But what if we could create and sustain such a stellar inferno right here on Earth, not as a weapon, but as a virtually limitless source of clean energy? This is the monumental challenge of nuclear fusion, and it requires us to build a star in a bottle, achieving and controlling temperatures that make the core of the Sun seem almost temperate by comparison. Experimental reactors like tokamaks and stellarators are designed to heat hydrogen fuel to a staggering 150 million degrees Celsius, a temperature necessary to force atomic nuclei to overcome their natural repulsion and fuse together, releasing immense energy in the process. The fundamental challenge is one of confinement. At 150 million degrees, any known material would instantly vaporize. The fuel is in a state of matter called plasma, a searing soup of free electrons and atomic nuclei. To handle this, scientists use a cage of pure force, magnetic confinement. In a donut-shaped tokamak reactor, incredibly powerful superconducting magnets generate twisting magnetic fields that act as invisible walls, suspending the superheated plasma in a vacuum away from the physical reactor walls. The plasma, being made of charged particles, is forced to follow these magnetic field lines, spiraling around the torus without touching the sides. It's an astonishing feat of engineering, using some of the strongest magnetic fields ever created on Earth to bottle a miniature sun. An alternative approach, known as inertial confinement, takes the opposite tactic. Instead of trying to hold the plasma stable for a long period, it aims to create fusion conditions in a tiny, fleeting burst. The National Ignition Facility in California uses the world's most powerful laser system, focusing 192 beams onto a peppercorn-sized pellet of frozen hydrogen isotopes. In a fraction of a blink of an eye, the lasers deliver a crushing blow, heating the outer surface of the pellet so rapidly that it explodes outward. According to Newton's third law, this explosion forces the rest of the pellet to implode inward with incredible force, compressing and heating the hydrogen fuel to conditions even more extreme than those at the center of our Sun, triggering a miniature fusion explosion that lasts just a few trillionths of a second. Both of these methods are monumental undertakings, pushing the boundaries of physics, material science, and engineering. The goal is to achieve ignition, the point where the fusion reaction becomes self-sustaining, producing more energy than is required to heat and contain the plasma. While the temperatures involved are beyond everyday comprehension, the potential reward is a transformative energy source fueled by abundant hydrogen from seawater, producing no long-lived radioactive waste and no greenhouse gases. It's the ultimate act of cosmic mimicry, a testament to our desire to not just observe the universe's most powerful forces, but to understand and ultimately harness them for the benefit of all humanity. But our exploration of stellar extremes cannot be complete without meeting the true aristocrats of heat, the stars that define the upper limits of normal fusion. These are the O-type stars, the blazing blue-white giants that serve as the universe's ultimate heavyweights and thermal powerhouses. With surface temperatures ranging between 30,000 and 50,000 degrees Celsius, they are so profoundly hot that if one were to replace our Sun, its sheer radiance would vaporize Earth's entire surface in an instant, transforming our planet into a scorched cinder almost immediately. What makes these stars so unimaginably hot begins with their immense size and mass. An average O-type star is born with a mass at least 15 times that of our Sun, and some can exceed 100 solar masses. This incredible bulk creates a gravitational force in their cores so intense that it drives the nuclear fusion furnace at a truly frantic, almost desperate pace. They don't just burn hydrogen, they devour it. The core pressures and temperatures are so extreme that they fuse their hydrogen fuel via the carbon-nitrogen-oxygen cycle, a far more efficient but vastly more rapacious process than the proton-proton chain that powers smaller stars like our Sun. This furious rate of energy production is what floods their immense surfaces with such blinding, high-energy light, pushing their thermal emissions deep into the ultraviolet and even soft X-ray parts of the spectrum. This profligate spending of fuel comes at a steep cost, a shockingly short and violent life. While a star like our Sun will burn steadily for 10 billion years, a massive O-type star lives fast and dies young, exhausting its entire hydrogen fuel supply in just a few million years. Their existence is a brief, spectacular flash in the cosmic pan, a stellar drama that unfolds on a timescale shorter than the reign of the dinosaurs on Earth. Their fate is sealed from birth. Such immense stars are destined to end their lives in the most cataclysmic way possible, as supernova or even hypernova, scattering the heavy elements they forged in their cores across the galaxy to seed future generations of stars and planets. The influence of an O-type star, however, extends far beyond its own fiery surface, dominating the celestial neighborhood for light years in every direction. Their most powerful tool is their incredible output of ultraviolet radiation, particularly in the high-energy Lyman-Werner band. This radiation is so intense that it acts like a cosmic blowtorch, capable of photoevaporating nearby gas clouds. It strips electrons from hydrogen atoms in a process called ionization, creating vast glowing bubbles of plasma known as H-II regions, like the iconic Orion Nebula. These expanding bubbles can actually compress adjacent regions of a molecular cloud, triggering the collapse and birth of new stars, making O-type stars both destroyers and creators of worlds. For any fledgling planetary system unlucky enough to form within a few light years of such a behemoth, the presence of an O-type star is an existential threat. The relentless UV radiation burns away the light, gaseous envelopes of young gas giant planets, halting their growth and potentially leaving behind only stripped-down rocky cores. It can also break apart the complex organic molecules that are the precursors to life on the surfaces of protoplanets, effectively sterilizing entire swaths of a star-forming region. The habitable zone around a star itself is dramatically reshaped by this external radiation. A planet that might otherwise enjoy temperate conditions could have its atmosphere scoured away by the harsh glare of a distant O-type neighbor. These stellar titans are therefore the ultimate architects of their galactic environment, their fierce light carving out cavities in nebulae, catalyzing new star formation at their edges, and setting harsh but necessary boundaries for where life might one day have a chance to emerge. But for all the extreme temperatures we find bound within stars, nebulae, and planets, some of the most staggering thermal equivalents in the universe are not contained in any one place at all. Instead, they are carried by single subatomic particles screaming across the interstellar void. These are ultra-high-energy cosmic rays, and while they themselves don't have a temperature in the traditional sense, the energy they carry is so astronomically vast that if we could convert their kinetic energy into thermal energy, it would represent an effective temperature in the billions of degrees. This isn't heat you could feel, it's a measure of pure, unimaginable motion, a testament to the universe's most powerful and enigmatic particle accelerators. To understand this concept, we need to think about temperature at its most fundamental level. What we perceive as heat is really just the frantic jiggling and vibration of atoms and molecules. The higher the temperature, the faster they move. A single particle, like a proton, doesn't have a temperature itself, but it does have kinetic energy, the energy of its motion. An ultra-high-energy cosmic ray proton is moving so incredibly fast, at over 99.9999999% of the speed of light, that its kinetic energy is beyond comprehension. The most energetic cosmic ray ever detected, nicknamed the "Oh my God" particle, carried the kinetic energy equivalent of a well-thrown baseball, all packed into a single, minuscule proton. If you could somehow stop this proton dead in its tracks and convert all that motion into random thermal motion of a group of particles, you would create a plasma with a thermal temperature measurable in the billions of degrees, rivaling the conditions in the most powerful supernova. The origins of these incredible particles is one of the greatest outstanding mysteries in astrophysics. Their immense energy means they cannot be easily confined by the Milky Way's magnetic field. They should mostly come from outside our galaxy. Yet, pinning down their exact source is incredibly difficult because they are electrically charged. As these charged protons and atomic nuclei streak across the universe, they are deflected and bent by the magnetic fields that permeate interstellar and intergalactic space. By the time one finally slams into Earth's upper atmosphere, creating a vast shower of secondary particles that we can detect, its path is so scrambled that tracing it back to a single point of origin is nearly impossible. It's like trying to find the source of a single leaf blown into your yard after a hurricane. Its journey has been so chaotic that its original location is completely lost. The energy requirements to accelerate a particle to such velocities are almost unthinkable, ruling out most common cosmic objects. The usual suspects, supernova remnants, pulsars, and even active galactic nuclei struggle to account for the very highest energy events. Scientists are now investigating the most violent phenomena imaginable as potential sources. Top contenders include cataclysmic events like gamma-ray bursts, the merging of supermassive black holes, or immense shock waves traveling through galaxy clusters. Some theories even point to more exotic sources, like the decay of bizarre cosmic strings or other defects in the fabric of space-time left over from the Big Bang. Each detection of one of these ultra-high-energy particles is like a tiny, hyper-energetic postcard from a cosmic catastrophe of unimaginable proportions. But it's a postcard with the return address mysteriously blurred beyond recognition. The study of these particles is a field known as particle astrophysics, and it requires some of the most unique observatories on Earth. Since the particles themselves are rare and directly hitting the ground is even rarer, scientists don't try to catch the primary particle. Instead, they build massive detector arrays to capture the expansive shower of secondary particles created when the cosmic ray collides with an atom in the upper atmosphere. Facilities like the Pierre Auger Observatory in Argentina cover 3,000 square kilometers with 1,600 water tanks, waiting to detect the faint flash of Cherenkov radiation as these secondary particles pass through. By studying the size and shape of these immense air showers, physicists can work backwards to calculate the stupendous energy of the original cosmic ray, giving us a glimpse into the workings of the universe's most powerful engines, all by observing the microscopic fallout from a single universe-spanning particle impact. After exploring the billion-degree signatures of cosmic rays and the artificial suns of fusion reactors, we arrive at a thermal frontier that hits much closer to home, the astonishing, life-giving resilience of biology itself. We've marveled at temperatures that vaporize planets and freeze atoms solid, but life on Earth operates within a far narrower, yet incredibly adaptable window. The true extreme isn't just the environment, it's the fact that anything can thrive there at all. From the permanently frozen deserts of Antarctica to the crushing, superheated depths of the ocean floor, life has found a way to not just survive, but to flourish, pushing the very definition of what we consider possible for a living organism. In the bitter cold, the record holders are certain species of bacteria and algae that make their home in the sea ice surrounding Antarctica. These organisms can remain metabolically active at temperatures as low as -20 degrees Celsius. They achieve this through a clever biochemical trick, producing special proteins and antifreeze agents that lower the freezing point of their own internal fluids, preventing the formation of sharp, cell-shredding ice crystals. They essentially surround themselves with a natural, non-toxic antifreeze, allowing their cellular machinery to continue functioning in a state that would be fatal for most other life. Their metabolism doesn't stop, it just slows to an incredible degree, entering a state of suspended animation where they can wait for centuries for a brief thaw to grow and reproduce. This isn't merely enduring the cold, it's a masterclass in biochemical engineering for survival. On the opposite end of the spectrum, the current high-temperature champion is a microbe known as Methanopyrus candelari strain 116, a type of archaea discovered thriving in hydrothermal vent systems on the seafloor. It doesn't just tolerate heat, it requires it, growing best at around 122 degrees Celsius and capable of surviving brief exposure to temperatures as high as 130 degrees. At this heat, water remains liquid only because of the immense pressure from the ocean above, preventing it from flashing into steam. For an organism to exist here, every single component of its cellular structure must be reimagined. The cell membrane is built from unique lipids that are branched and fused together, creating a sturdy, heat-resistant barrier more stable than soap bubbles. Its enzymes and other proteins have incredibly robust, compact structures, held together by a stronger network of bonds and often stabilized by extra ions to prevent them from unfolding and denaturing into useless tangles. Even its DNA is protected by special proteins that act like molecular chaperones, constantly refolding it to maintain its crucial double helix structure against the relentless thermal assault. What makes these adaptations so revolutionary for astrobiology is that they fundamentally rewrite the rules for where we might find life beyond Earth. For decades, the search for extraterrestrial life was largely confined to the Goldilocks zone, around stars, the region where temperatures are just right for liquid water to exist on a planet's surface. The discovery of extremophiles, organisms that love extremes, has dramatically expanded that search area. We now look at the frozen subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus not as dead, icy wastes, but as potential refuges for life similar to Antarctica's cryophiles, warmed by tidal forces and protected from the harsh vacuum of space. Similarly, the ancient wet past of Mars or the hypothesized subsurface oceans on distant dwarf planets like Pluto are now considered viable targets. The heat-loving archaea suggests that even within our own solar system, the volcanically active moons like Io, or the hypothesized hydrothermal vents in the subsurface ocean of Enceladus, could provide the chemical energy and stable, hot environment needed to sustain an entire ecosystem completely independent of sunlight, just as they do in the darkest depths of our own oceans. Life, it turns out, is not a delicate flame to be sheltered, but a tenacious force that can exploit the energy gradients found at the most extreme thermal boundaries, forcing us to look everywhere with new and far more hopeful eyes. From the near-perfect stillness of absolute zero to the fleeting, universe-forging inferno of a 1 trillion-degree gamma-ray burst, our journey through the cosmos has revealed a thermal spectrum of almost incomprehensible breadth. We've witnessed how cold is not merely an absence, but a creative force that patiently assembles the building blocks of stars in frozen molecular clouds, and how heat is the engine of cosmic evolution, from the steady burn of our sun to the cataclysmic death of stellar giants. Each extreme temperature, whether sustained for billions of years or flashing into existence for a microsecond, plays a crucial and specific role in the grand narrative of the universe, shaping the formation of elements, the birth of planets, and the very laws of physics as we understand them. This incredible range challenges our earthly perceptions and forces us to think in terms of cosmic scales. The forces that allow a microbe to thrive in boiling water or a neutron star to cool over eons are governed by the same fundamental principles that dictate why your coffee gets cold. By studying these limits, we don't just catalog astronomical records, we probe the deepest questions of existence. The quest to understand the corona's mysterious heat refines our knowledge of magnetism and plasma. The effort to create a quark-gluon plasma in a laboratory tests our models of the universe's first moments. Each temperature extreme is a natural laboratory, offering a unique window into the behavior of matter and energy under conditions we could never replicate fully here on Earth. The story of temperature is ultimately the story of energy transformation from gravitational potential to thermal radiation, from nuclear binding energy to the kinetic motion of particles. It is a story that connects the vast and distant to the intimate and familiar. The gold in a wedding ring was forged in the unimaginable heat of a supernova, while the oxygen we breathe was released by stars that lived and died long before our sun was born. We are, all of us, children of these cosmic extremes, our very bodies made from elements cooked in the most violent ovens the universe can provide. Now we turn the conversation over to you. With 30 astonishing facts to choose from, which one reshaped your understanding of hot and cold? Was it the chilling efficiency of the Boomerang Nebula, nature's own cosmic freezer? The paradoxical heat of the sun's corona that defies all intuition? Or perhaps the mind-bending notion that the coldest place we've ever created is right here on Earth, in a lab cooler than the void between galaxies? Share the fact that amazed you most in the comments below. We read every single one. Our journey through the universe's thermal extremes doesn't end with what we know today. Some of the most thrilling discoveries lie just ahead, powered by a new generation of missions and technologies designed to probe environments we've so far only been able to theorize about. The next frontier of thermal science is already taking shape in laboratories and on launch pads around the world, promising to send us deeper into both the hottest and coldest realms of physics than we have ever ventured before. One of the most anticipated missions is NASA Da Vinci, scheduled to descend through the thick Venusian atmosphere to finally understand the true nature of our sister planet's infernal surface. While we know it averages a scorching 465 degrees Celsius, we have very few direct measurements from the surface itself. Da Vinci's specially hardened descent sphere will do more than just take the temperature. It will analyze the atmosphere's composition at different altitudes, revealing precisely how the runaway greenhouse effect operates in such brutal detail that it will refine our climate models for all planets, including Earth. This isn't just about visiting a hellscape, it's about uncovering the precise chemical and physical processes that can push a world into such an extreme state, giving us critical insights into the delicate balance that makes a planet habitable or not. Meanwhile, in the realm of pure energy, facilities like the Electron-Ion Collider, currently under construction at Brookhaven National Laboratory, are being designed to go far beyond the 4 trillion degree records already set. Its goal is not just to create quark-gluon plasma again, but to precisely control and study it in unprecedented detail. Scientists want to understand how this primordial soup flows, how it transitions back into the normal matter that makes up our world, and to map the strong nuclear force, the fundamental glue of the universe under these extreme conditions. This research could literally allow us to freeze frame the universe's first millionths of a second, providing a direct window into the moment the very first protons and neutrons were born from the cooling fire of the Big Bang. The quest for absolute cold is also advancing at a breathtaking pace. The Cold Atom Lab aboard the International Space Station is already producing Bose-Einstein condensates in the microgravity of orbit, where atoms can be manipulated and observed for much longer periods than is possible on Earth. The next step is to push these condensates to even lower temperatures, perhaps down to a few picokelvin, to observe exotic new states of matter and quantum phenomena that are completely invisible under normal conditions. These experiments could revolutionize our understanding of quantum mechanics, potentially leading to entirely new technologies based on quantum sensors that are orders of magnitude more sensitive than anything we have today. And looking even further out, the James Webb Space Telescope is already giving us a new perspective on thermal extremes across the cosmos. Its incredible infrared sensitivity allows it to peer into the hearts of stellar nurseries to measure the faint heat signatures of the earliest stages of star formation, and to analyze the atmospheres of distant exoplanets, categorizing them not just as hot or cold, but by their precise thermal structure and composition. This data will help us find truly Earth-like worlds by identifying those with temperate, stable climates, while also revealing the most violent and extreme planetary environments in our galactic neighborhood. Each of these ventures, from the planetary to the subatomic, represents a new chapter in our story of exploration, proving that the universe's thermal secrets are far from fully revealed.